Hopefully you found the intervals on which these functions are continuous. We have f of x, g of x, and h of x as our functions. I'm going to go ahead and do these. It's a little easier to talk about where these are not continuous sometimes. So if you think about this, we don't want our denominator to be 0. And also, we don't want our denominator to be a square root of a negative number. If you think about those two things in tandem, that means that the square root of x minus 4 needs to be greater than 0. So that's essentially our domain. And what that means for us is that x minus 4 has to be greater than 0. Just one way to think about that is square both sides. They're both positive square roots, so you can square both sides. And therefore, x, add 4 to both sides, has to be greater than 4. So the domain is when x is greater than 4. So we're continuous on the interval from 4 to positive infinity. For g of x, well, there is a problem when the denominator is 0. X squared minus 3x minus 10. There's a problem when that is 0. This problem is a problem of factoring. So we can factor the x squared minus 3x minus 10 into x minus 5 times x plus 2. And so there's a problem at two places. There's a problem when x is equal to 5 and when x is equal to negative 2. In terms of my intervals on which this is continuous, this means that we are continuous, or I should say the function is continuous, on the interval from negative infinity up to negative 2. Not at negative 2, but after negative 2, it picks back up and is continuous up until 5. It's not continuous at 5, but we pick back up afterwards, and it's continuous from 5 to positive infinity. So we're not continuous at negative 2 or 5, but everywhere else we are continuous. In terms of my last function, h of x is equal to secant. Remember, secant is simply 1 over the cosine. And so we have a problem when the cosine is 0. And we did that one in our tangent. So notice that secant and tangent are going to be continuous on the exact same intervals. So the domain is going to be all real numbers except when cosine is 0. And when is cosine 0? Well, cosine is 0 when we have k times pi plus pi over 2, where k is an integer. And so we're continuous on all of these intervals, but we have to be discontinuous every time we stop at some integer times pi plus pi over 2. We can also see that through the graph if we'd like. So I've graphed the secant function, and you can see at each place where we have k times a pi over 2, we have these weird asymptotes, lots and lots of asymptotes. Let's see if I can draw one. There you go. There's pi over 2. And so you can see the asymptote here at x equals pi over 2. And if we did x equals negative pi over 2, you can see another asymptote. And you can see that in each little section here, the function is continuous, but you're skipping between asymptotes. And that's what happens for secant of x.